Hi, this is Jeff. Thanks for tuning in to part 2 of the Commodore 64 power supply series. Last episode we looked at the various power supplies I had on hand and the common failures that can occur with them. This episode we're delving into the innards of these power supplies to see what makes them tick and what makes them stop ticking. I thought we would start looking inside the early repairable Commodore power supply, as it will be easy to identify all the parts and compare it against the available schematic. It is also the easiest one to take apart. Then we'll disassemble the epoxy brick versions and see what parts they are using and how they compare. Commodore did make an early fully repairable C64 power supply. I got lucky and bought a C64 system from the original owner, which came with this supply. As you can see, the repairable unit is about the same size as the more common black brick. While the brick has a red top case, the repairable supply has sloped sides and a vented case. There are 4 number 1 Phillips screws on the bottom, 1 in each corner, which you'll need to remove to split the case. Let's get this cracked open and see what's inside of it. Here we have the voltage regulator on the left and the transformer on the right. I thought it was strange that the wires go up and over the heatsink like this. When there's the notch, it looks like it was made for that purpose, but the wires are not long enough to reach the slot. Here is a look at the transformer itself, and you can just see the fuses and rectifier diodes. Here is the inside of the bottom cover. And we have the top cover. Here's the inside. You can see the vents there, and here's the outside. And we'll flip it over and have a look at the label. Here is the voltage regulator section of the power supply. We can see a big capacitor, the voltage regulator that's bolted to the heat sink, a little resistor, and a small capacitor. And we've got a transformer that the fuses are mounted directly to it, as well as the rectifier diodes, which is kind of a different type of arrangement. The values of all these will be in the schematic that we'll look at in just a little bit. And on the back of the transformer is the manufacturer's name and the power supply. One other interesting thing with this power supply is that it has all 7 pins in the DIN connector, whereas your typical brick type power supply only has the 4 used pins. I just thought that was kind of curious. Now that we've had the tour inside the power supply, let's compare the schematic along with some pictures of the power supply so we can get an idea of what parts on the schematic correspond to the real physical parts inside the power supply. So we'll start from the left hand side of the schematic here, and this is the schematic symbol for our transformer. We have our primary mains voltage coming in here, which in this case is 117 volts, and we have 2 secondaries, which is lower voltage in this case. The first one here on the top that I'm circling is for the 9 volt AC output. It goes through a 3 amp fuse. Over here to the right on the picture, that is this fuse right here, and you can't see the wires, but right here they go for the 9 volt AC output. That's all there is to that. And back over on the schematic here on the other secondary, you can see this one looks a little different. This winding has a center tap, so it's got another wire connected right to the center of that winding, and it's going through 2 diodes which rectify the AC into DC, and it has its own fuse on the common here. And if we go over to the picture here to the right, we can see our 2 diodes and our fuse. Now, one thing I'd like to point out, you see the stripes here on the bottom of these diodes? That's called the cathode. And we see the same thing in the schematic. So you can look at the schematic and see which way the diode should be positioned and See the same thing in the image. Now back over in the schematic, we see we should have a 4700 microfarad capacitor next. So let's go till we get a good picture of the board. Here we go. And yeah, here's our 4700 microfarad capacitor, 16 volts. That's what the schematic calls for. And our next thing in line, looking back over at the schematic here, is the voltage regulator, which in this case is an SK3052P. The schematic symbol they're using here is a transistor, but it is a voltage regulator. There's lots of different transistors and whatnot inside of it. So looking over on the right at the picture, we see, well, there is our voltage regulator mounted to the heatsink. This is a pretty good voltage regulator. It's rated at 2 amps maximum, which is more than what we're using from it. It does not have thermal protection, but it does have good overcurrent protection built in. So all in all, it's a fairly decent regulator for this. And the next thing we have after the regulator is a 47 microfarad 10 volt cap, which is this guy right here. Now you notice this little blue looking resistor laying right here. That is this 300 ohm resistor that's connected to the ground pin of the voltage regulator. What that does is it pulls that ground pin for the regulator slightly above ground, and it makes the output here slightly higher than 5 volts. So it'll be about 5.1 volts, and that just takes care of any voltage drop in the wiring or in the switch, of the C64, that type of thing, to make sure we're getting 5 volts to all the components. One other thing to point out here, over in the picture on the right hand side, is the size of this heat sink. That's a pretty good size. According to the schematic for the voltage regulator, you would want around 8,000 millimeters square for the power dissipation this is going to see, and this is close to that size, and the case is ventilated, so I'd say they did a pretty good job sizing that heatsink for this application. Had poor regulation, and we will take a screwdriver, pop the case apart, and then attempt to use this wooden form here. At this point, I also grabbed an 1.5 inch wide scraper to assist in the prying with the cover off with. I have some posts here which are kind of holding it together, and of course, as you see here, we have a big block of epoxy. Let's see if we can get that closer and saw it. Okay, here we go. We've got the macro focus turned on, so you can see our AC inners here. And we can see AC inners here. We've got ground and neutral and hot. And here we've got our power wires going out to the C64. Should be 4 of those. Yeah, there we are. 1, 2, 3, 4. These are some leads from the transformer. You can see right here is a fuse. Back in the day I was able to chip that fuse out of there and replace it, but pretty much this epoxy makes this virtually impossible to work on. Here I'm wanting to remove the power cable in and out of the brick, so I'm chipping away the epoxy so I can cut all the leads as long as possible. had to chip away the epoxy a bit to get our AC leads here as long as possible to get them out of there. And then I took the putty knife / scraper and went gently along the edges to try to break them free as much as possible. You know, this type of thing. Now, our brick without the leads will fit down snugly in here. Hold your mouth just right. And I found when I made this, I had some 1x2 or 1x3s sitting out in the garage, and if I cut them 4 5/8 long, all four at the same size, they screwed together perfectly to hold it. My workbench was not sturdy enough for banging on, so try number 1 was a piece of cardboard on the floor, which did not work. Okay, so using the cardboard as a place to hit didn't work, so I got an old piece of wood, which I think was from a pallet, and I put some gloves on because it was going to hurt my hands, and we'll try it again. Hey, look at that. It's coming loose. Hey, we've got it out of the case. Almost, oops, I bet you can look down here better. Got it out of the case. Almost complete. And there is the block of epoxy with the stuff in it. As I started to film this, of course my camera batteries died right away. And while I had this sitting on the bench, some of the epoxy around the transformer here seemed to be pretty easy to chip off there. So I spent about 10 minutes and popped off what I could very easily. And I was afraid of breaking the 3 leads from the transformer here off. So I thought, well, those go right into the circuit board here. Maybe we could just heat those up, melt the epoxy a little bit, and pop those out so we can get a better look. You can see what a mess it made chipping that off there. Got the soldering iron fired up here. And I'll grab some pliers. Okay, that works. Get the iron over alongside the wire. Wait for the epoxy to bubble. We can reach it up. There. Okay, so now we have the transformer section, which is the heavy bit, separated from the regulator section. Don't know if this is going to be useful because this is still a big block of epoxy, but we will see. Okay, thought we would get a bit of a better view here of the transformer. Now the AC power enters here. You can just see where I cut the leads off. It solders to these 2 posts. Here is the fuse on the secondary side. And these 2 insulated black wires right here are where the 9-volt AC would come out. And these 3 wires, these 2 twisted together, and this one, is where the AC comes out to go into the regulator to get converted to 5 volts DC. Next, I'll see if we can't figure out a way to get some of this cleaned out of this voltage regulator. Right now it's just a solid block of worthlessness. I'm not sure what the best way of trying to clean all this epoxy out is. It's probably not possible to do without destroying the circuit board, which is not that complicated anyhow. You can get a paint remover slash epoxy remover. The problem is it also will melt wiring and the enamel on transformers, so you can't use it to try to clean up the whole thing. The circuit board is right here, so we don't want to pound too much right there, so I think I will just try whacking it right here. See what happens. Yeah, that's not too effective actually. See, it's not really stuck to the aluminum so much. So now what we have is this whole thing, the whole epoxy block is stuck to the heatsink because of this screw right here. Sorry, I moved that suddenly, you might not be able to see it. And that part is soldered right here. So I'm not exactly sure what. That stuff is a mess. Really surprisingly, this is coming off the circuit board quite easy. I'm not trying to dig into the circuit board. I'm just not trying to go down to the board, just trying to go right onto the epoxy. Take our solder sucker here and okay, that should have got us loose of that regulator. Hey, look at that. We got the regulator off the rest of the board, and interestingly, the part number is on the epoxy. See if I can get you a picture of that. So interestingly, the part number of the voltage regulator came out in the epoxy, and here it is. Okay, I got a little excited and broke away all of the epoxy from the circuit board and broke the circuit board in the process. But I did find out by luck what components were in here. You can see the two rectifier diodes, one of which I broke. I couldn't find any markings on these. This is where the voltage regulator was. This component, I'm not sure what it was. I couldn't find it in any of the epoxy chunks. I basically squeezed the big chunk of epoxy in bench vise and until it cracked into little bits, and kept doing that. Here is the big regulator cap, which was right there. That was a 4700 microfarad 16 volt.
85 degrees C. There is a 100 ohm resistor here, a 2.2 ohm resistor here, and this is a 2.2 microfarad 16 volt tantalum. The interesting thing was, on the capacitors, I could not read the value on the package once I got out of the epoxy, but the print, if you can see that, actually stuck on the epoxy. That's how I know that was a 4700 microfarad capacitor. And on the tantalum, don't know if you're going to be able to see that. Okay, there you can see the 2.2 written backwards. So this is a whole lot like the schematic for the old power supply. It's a center tap secondary transformer, so you only need 2 rectifier diodes. But the interesting thing is that if we look at the transformer here, this is AC in, so this is our 110 volt in. Here and here is our 9 volt AC out, which goes through this fuse, which I did not find the value of, but I bet it's 1 amp. And here are the 3 leads going to the DC. So this is the center tap, which becomes the common, and these 2 are what goes through the diodes. You can see, just taking it apart, trying to take it apart this far, I've destroyed the transformer. But the interesting thing here is that there is no fuse on the DC side. So only the AC output was fused, which is kind of interesting. Okay, this was the elusive piece of epoxy broken loose from the black brick. You can just see, if I can spin this around here, these 2 leads sticking up from what I believe to be a capacitor. So, okay, so what I've done here is hook up test leads that go to this little contraption, which is a component tester. You see these kits on Banggood and whatnot. This is an older one with just a character display. It doesn't have the fancy graphical display. So if we turn this on, it'll go through and it identifies it as a capacitor about 231 nanofarads. So that gives us an idea that it is a capacitor, and we can see if we can chip it out of there and confirm that value. Okay, part of the way through the electronic archaeology project here, chipping the capacitor out of the stone, or epoxy in this case. You can see it does look like a little tantalum capacitor, and we'll see if we can get the rest of the way out of there without breaking. Okay, got it chipped out of there. See if I can get it to here where you can see it. It does indeed say 0.22, so the little component tester did a pretty good job.
The next thing I did was to look at the front of the PCB and the back of it, and I made a sketch from the top as though I were looking with X-ray vision through the PCB. So I had a layout like you normally would in a circuit board design package, and drew in the locations of the components and noted their values. And so you can see here's the back view. It's still partially blocked by some epoxy I couldn't get chipped off there, so I'd use an ohm meter in some places, and drawing out the traces like this since this was a simple board, was not too much trouble, and it gave me an idea of how things were routed under the epoxy. Then the next thing I did was create a more of a schematic view representation of that, where the wires came in, where the different parts were. This is still kind of laid out in the positions they were on the board. And of course this looks almost like the repairable power supply we first looked at. It's really close. So I took that schematic and just marked it up, made a mark that there was no fuse in here. There's some resistors and capacitors at different values in different places, but it's pretty close. The thing that really struck me with this power supply is that the regulator was the generic GL 1016, which I couldn't find a data sheet on, and I'm suspicious that it was a cheap kind of off-brand part that may not have been as good as the previous SK part. And the transformer was quite a bit smaller than on the repairable power supply, and we'll get into that a little more later and see if we can figure out electrically how much difference that made. I thought, since these white bricks were rated a little higher than the black bricks, we might pop one apart and see if the parts are different. So essentially this is going to be the same as the tearing apart the black bricks, so nothing terribly exciting. Okay, so you can tell right away that the inside of the back cover is different. If we look in the brick itself, you can see that it's a bit of a different layout. So we'll see if we can pop that out of there and see what's going on. That's my cat there who decided to join in. Okay, I've modified the approach here a little bit. I cut some notches in the fixture to let the cord pass through, because I didn't want to disconnect the cord from this one. I'll set it here like that with some slack underneath it. Place board on top. Driving it through. That's okay. So what I resorted to here is a couple quick clamps to hold this together tightly along here so these ribs will catch. Well, it's not falling down to the fixture this time, but I also don't see it coming loose.
Okay, this wouldn't work the same way the black one did, so I took my screwdriver and carefully chiseled around here to try to loosen things up. Desoldered the leads from the transformer to the circuit board, and let's see if I can get you a close-up of what that looks like now, like that. And now I'm trying to tease this voltage regulator section out of here. There we go. One solid block of heatsink. Okay, this is what it looks inside. The voltage regulator section pried out of there. I'm going to keep the transformer part in there. And desolder the wire, the ground wire, from here. Nope. And I think this transformer looks much larger, or at least 25% or so larger than the black brick. So I'll get this desoldered here and we'll see what we can find inside the voltage regulator. Okay, I think we'll do sort of like we did on the black brick, and we'll desolder the voltage regulator and leave it on the heatsink. Wiggle the pins to make sure that they are disconnected. Well, color me surprised that that screw came out of there. Heatsink, epoxy bloxy. Yeah, this looks quite different. Okay, after about an hour of heating and chipping all that epoxy off there, this is what we have. I broke the fuse. This is completely different than the black brick of death. We have two separate coils coming off there. The fuse is on the AC side like before. The DC side is using a full bridge rectifier. This is an actual Thompson SES 7805. 4700 microfarad, a couple smaller caps, and a couple resistors here.
The next thing I did was to draw a little sketch which shows the components in their places from a top view of the board, as well as their values. This is where the transformer connections are. You can see that they've kind of skipped a hole here, so you've got the first and third are for the 5-volt regulated supply, and the second and fourth are for the 9-volt, which was kind of odd, I thought. And if we look at the image of the regulator, we can see, the diode section here, the fuse, the big capacitor, voltage regulator, just like on the sketch here. Now, I said before that the voltage regulator was a 7805, and it is, but it's an SCS Thompson part. It's a 78S05CV, and that is important, as we'll see in a bit. Then I drew up a schematic based on my previous sketch, which is standard voltage regulator schematic. We have the 9-volt AC right here through a fuse, just like we did on the black brick. Since we don't have the center tap on the transformer this time, it's using a full bridge rectifier. And kind of an odd thing is it has these, I think they're 0.1 microfarad caps across each diode. That's some sort of snubber. It's a pretty old-fashioned idea as I understand it. I've never seen that implemented like this before. We've got our big bulk capacitor, and this one had another little capacitor going across the voltage regulator. We've got a pair of resistors here which bumps up the output voltage from 5 volts to about 5.2 volts, and then the smaller 4.7 microfarad cap. So all in all, pretty standard, laid out well, good choice of components. The caps were 105 C rated. The voltage regulator is a very nice part, which we'll look at next. Okay, here we've got a clip of the data sheet for this regulator. You can see it's an SCS Thompson, or ST as they're known now, part. It's an L78S series, and this is a 2 amp regulator. And of course, output current up to 2 amp, available on a lot of different output voltages. This part has thermal protection and short circuit protection. So this is a pretty good regulator. All in all, I would say that the white brick is a pretty good design, and I would not be afraid of using it on my Commodore 64, provided I checked the outputs and checked them under load. It's a pretty good unit. In order to compare these 3 power supplies, I made up a little table here showing each supply, the dimensions of the lamination, which is approximately the core size of the transformer, the approximate heat sink area, the weight in grams, and then using this graph and formula, which I found on a website, which I'll link to below, I calculated the theoretical maximum wattage that the transformer could handle. And so we'll see here on the repairable that it's about 36 watts. And if we look here at the schematic that we have for that one, it's showing that it's a 40 watt transformer. So our formula is pretty close. It gets us in the right ballpark. Looking at the other 2 transformer, the black brick is much lower, about a third lower than the repairable, and the white brick is about the same as the repairable. And this correlates to what it looked like visually, that the black brick was about 25% less in volume than the other 2. So I found that kind of interesting. The black bricks smaller transformer combined with the smaller heatsink area leads me to believe that it was really undersized for the job it was supposed to do, which probably led to the high failure rate that we're seeing back when they were new and over the years, because they've run so hot trying to keep up with what people are asking them to do. So coming up in the next video, which would be episode 3 of this power supply series, we'll look at the Phoenix CPS 10 power supply, and we'll kind of add it into our table here once I'm able to weigh the transformer and take some measurements and that type of thing. And we'll see how it's built, what parts are inside of it, and how it stacks up to our other 3 power supplies here. So stay tuned. We'll see you then.